right, and head it over to Douglas.
All right. Well, thank you, Melissa. I'll share my screen here. Let me switch over to, uh, oops, let me open that up so I can still see that. Uh, the slideshow mode. All right. Well, thank you. My name is Douglas Tucker. I'm a member of the community science team. I'll be talking about image access and display. And also I will put the link to this session slides in the chat. So if people wish to access those, they are available in the chat window. Um, so let's move along. So okay, this is the last session of this last talk of the last session of the Ruben Data Academy. Uh, you've seen this before. I won't go into this, but all the recordings will appear on the for future reference. All the recordings from the Data Academy will appear on the Data Academy webpage for well, as I said, for future reference. So I won't. I'll just gloss over this and move on. Um, so session number 6. We are looking at image access and display. I will be using the Butler, SIA, and TAP to access images. And we'll see how to retrieve image cutouts and how to use Firefly for an interactive image display. And so we'll first have a few slides on when to use which. Then we'll look at some of the tutorial notebooks if the earlier previous session when we gave this talk this morning. Um, Probably won't get through all of these, but we'll try to get through as many as we can of the notebooks and possibly the portal tutorial. Um, let's see. So Ruben staff are here to help. We remind people, please, if you have questions, the community forum at community.lsst.org is the place to go. Create make new topics and Ruben staff out or anything that's in the support category. It'll be kind of like the reference for the future where people can search for that if they have similar problems, they'll be able to see what others have done in the past. This is kind of our archive of community information. Um, uh, just to mention also the Ruben data policy. It's listed on at ls.st/RDO013. So data right holders consist of scientists and students working or enrolled at U.S. or Chilean institutes and named members of international in-kind contribution teams. Only data rights holders may access proprietary data and services. And if you have any question of whether you're on the list or not, it's listed here at this website. This list is on this website. So proprietary data includes the annual data release, data products, images, and catalogs, and the prompt processed images for 2 years. And is accessed through the Ruben Science platform. What's publicly available is alert packets, and prompt catalogs. Things are done throughout the night, and all other data after 2 years, and of course all the documentation and support resources such as the community forum are public now. So they're there for you to use. Um, okay, let's move on to the topic of this particular session. So key concepts. When to use which service for doing image access? First of all, there's the Butler. This is recommended for image access via the notebook aspect. It's also recommended when the full image is wanted, including all the pixel information and the masks and so on. Uh, cutouts can cutouts can be made through a factory function, which we'll show later. There's also SIA and TAP services. So these allow you to grab a URL, an HTTP page where you can access the image, and they can pass that to the cutout service. And these are available through both the notebook and portal aspects. Um, and there's the cutout service. These only transfer the cutout portion, not the full image. And so these images are fairly big, and this is much more efficient if you only need a small portion of the image to use the cutout service. And then there's Firefly, which is an interactive image display that has built-in functionality for looking at the mask planes. So as I mentioned before, we'll look through some of these, as many of these tutorials as we can, hopefully both the notebooks, and hopefully we'll also get to the Portal tutorial. Rendered versions of of the notebooks are also available off the dp1.lsst.io website. Now, where they interact with the Firefly, they don't show everything because the Firefly doesn't really map well into the HTML rendered information. But you still get to see how things are run in the outputs, generally especially the catalog outputs. Oh, okay. So okay. So I know I went through this very quickly. Um, any questions at this point before we actually delve into the tutorials? All right. Well, uh, at the beginning of the session, there had been some issues with running things on data.lsst.cloud. That seems to be fixed. Frosty, our colleague Frosty went through and fixed things during the process of this past session. So if you'd like to follow along, you can go to uh, I'll even put it in the chat here. HTTPS data.lsst.cloud. So, and then and then you'll need to log in, and you'll want to go to the notebook aspect. I'll wait a few seconds while people do that. Let us know if you have any problems accessing your notebooks or the notebook aspect on the RSP server at data.lsst.cloud. Oh, and actually, I'm looking at the wrong one at the moment. Let's see. So we'll start. Um, anyone having any problems getting to data.lsst.cloud? All right, well, let's continue on. So I've actually opened up these tutorials already, but you'll want to go to the tutorials menu, go to the DP1 item on that, then go to the 100 series of how to use RSP tools sub-menu, and then to the 103 image access and display sub-menu. And we'll start out with 103-1 Butler image access. Let's click on that, and it'll open up in your Jupyter environment. Now, some of this has a lot of overlap with what Aaron was just showing us. I won't go into a lot of detail here, but we'll sort of see how to access. We'll look at accessing a deep coad and a visit image. As Aaron mentioned in the previous session, the Butler is the LST Science Pipelines interface for managing, reading, and writing data sets. It's also sometimes referred to as middleware. And it's recommended to use Butler when accessing image data in the notebook aspect. Here we just have a very short tutorial of how to access it. We saw a little bit of that before. Um, oops. So first of all, we'll import the Butler. We'll also import something called the time span to look at a range of times when we're looking at visit images. Let's open that up. Let's run this cell. Then we also want to open up Firefly. I've actually already opened it up, but let's do that again. And it is opens up in this in a separate tab. And for our use, we want to kind of you want to grab that with your mouse and pull it down here so you can see things side by side. All right, and let's see, where are we? Okay, so then we'll create an instance of the Butler, like we saw before, like we saw in the previous session, and we're looking at the DP1 repo and the collection called LST ComCam/DP1. So we open up that Butler, and then we want to query and retrieve images. Uh, so um, so we can Johnny, you want to constrain things by band or filter, sky location, and or time of observation. So there's 5 types of images that are available. There's the deep coad, which are stacks of multiple visit images. There's the template coad, which is like the deep coad, but they only use the best seen images, the top 1/3 seen images with the best seeing. Um, then there's a visit image. That's a processed and calibrated image from one visit by detector. And then there is the difference image, which is basically the visit image, visit image which has the template coad subtracted off. So you can look for transient objects or moving objects. And then also there is the raw, basically the exposure from the camera readout. We won't look at that, and we won't really look at the raw images here. There are some 200 level notebooks where you actually make use of the raw images, but we're just looking at the processed images. So first, let us grab a deep coad. And since a deep coad, I mean, it's a bunch of stacked images. It's a part of the sky. We're looking at so we want to find an RA deck and a band or filter to find a particular coad, a given tract and patch. Remember that that coads are that the LCD sky, Rubin sky is tessellated into tracks, and the tracks are subtessellated into patches. As Aaron was showing us in the previous session, we're looking at the extended Chandra Deep Field South, or ECDFS. And so so we choose a current near the center, an RA index near the center of the ECDFS, and we'll look for the R band. So we'll run this cell, and then might need to make this a little bit larger so we can see the whole query here temporarily. We'll create a query which looks for the band name, and we'll use this query function of patch region overlaps a point, and that'll be that ARIAN DAC. And so this is what our query will look like. And then we will use the Butler query datasets function to find dataset references for deep coad, which deep coads that meet the criteria from that query. And there'll be several there may be a few data sets which are returned there. We will grab okay, it's Python based. It's a zero index. We'll grab the zeroth or quote first of the return data sets to take a look at that. And now we can just display it in Firefly using afwdisplay.mtv. And generally, you'll get the image and you'll get all the mask planes covering it. But we want to remove the we want to look at the image. We'll set the mask plane transparencies to 100%. So it's all, the mask planes are completely transparent. So you just see the image data. All right, and that pops up here. So here we go. It's this is the full patch from this tract that we grabbed. The point that we aimed at is this yellow. That ARIA deck that we used to query it is this yellow circle here. Okay, so this is a nice coad. And now we can clean it up. Now we'll just image data takes a lot of space. We want to avoid using up too much space on our because we could end up I mean, this is pretty well. We're doing this intensively. Yeah, you'd have to watch out this for space, but it's it's good practice to delete things that you don't need anymore. So delete the query, the data sets reference, and that the deep coad from memory. Now let's take a look at visit images. So remember that's an individual. That's a image of a detector from a given visit. Well, in some ways, an exposure, but so it's a single epoch observation. We'll use the same RN as before, N band as we did before the coad. But this time, these are a lot of images taken over time, and we want to kind of constrain the time. So as we saw in the previous session, we'll use the International Atomic Time to define a time span. And we'll look at a 24-hour time span ranging from midnight of November 9th of last year to 24 hours later. And we kind of show two different methods of creating the timestamp. We have the calendar date, and we also use MJD here, and we create a time span that covers that range, the 24 hours. And then, okay, I'm gonna make this a little smaller again. You can see everything. We'll create a query to just grab things that overlap that time span and over that spot of the sky and for that given band, and we'll bind those things together to find and order things by the visit time span, by the start of each visit. And then, as we did before, we'll just grab like the 0th item on that list, that list of data references that were returned, and we'll define and we'll read it into a visit image, and then we can okay, I can make this move over here, and we can display it over here. And so this is a bit noisier because it's just a single observation, not multiple observations stacked together. When we presented this in the morning, one of our attendees noticed there's kind of a crosshatch pattern. This is due to parallel bias subtraction issues. It's known. But it's not a big effect, but something to be aware of. And then we'll clean these up. Now that's the end of that first notebook. And I know I went very quickly. Are there questions? Are people having problems? Are there any questions that people have they'd like to ask?
Hello, Douglas. I have a question.
Yes.
I downloaded the first image as a fit image, and when I visualize it with DCN9, it doesn't look like the same. It's like the color map. I cannot find the right color map to visualize.
All right, this will be something I would look at a little bit later, but if you go over here, actually we can do well, let's look at this pure image. There's so there's a color map things. Here's the overall color map of whether you're doing like black and white and invert black and white color mapping. You can modify the color here, but this is probably what you're probably most interested in is how things are how the contrast is done, how what the color stretch is, and here use a linear stretch to from 0 to 99 to the 99% highest pixel as black, white to black. Now you can change things. Uh, there's Z scales, which are probably more familiar to SAO image. It doesn't seem to have histogram equalization, but it does have many of the others. And you can also, I think, you can adjust things somewhat yourself, creating your own sampling. Oh, wait, there is histogram equalization. I did not know that. So you can play around with this. So there are options. All right. Any other questions? All right. So let's move on to the next one. We'll go to this to the 103.2, which you can grab once again from the tutorials, the DP1 menu, the 100 level submenu, 103 sublevel, and 103_2. It's the simple image access notebook. All right. So let's see. Okay, so Simple Image Access, or SIA, is a protocol of the International Virtual Observatory Alliance, or IVOA. Rubin has been very intentionally trying to keep to the IVO standards, so to make the data accessible, useful in different tools that use IVO, for instance, like TopCat. So that has been a goal for the Rubin software environment, is to make sure that things are IVOA compliant as much as possible. So SIA is it's a broadly used service used by different tools out there. When would you want to use a SIA service? Well, you can use it to find, retrieve, and display whole images based upon their spatial, temporal, and spectral coverage. It's good for quick access to images, pixel and header data, and for display and examination by eye. We recommend, if only a small part of the image, to use image cutouts, which you'll get to in the next tutorial. And if you want to look at if you want to do stuff with the science pipelines, do source detection and image analysis, we suggest that you just use the Butler in that case. And there's 200 level tutorials that go into that. Here we're looking at the SIA version 2 service, or SIA 2. So why don't we just jump in? So we'll import various things, including the SIA 2 service and PyVO. So read this in. We'll run this, and then we'll define parameters. I think these may be the same as before. These are probably, if not exactly the same, very close to the same as before. It's working in the extended Chandra Deep Field south near the center. So we look at the Aryan deck. We actually already opened that, but we'll just click on that again. We'll instantiate the SIA2 service using this code cell here. And then we want to query for images. So there's main constraints on that the SIA2 service queries use include position, coordinate, region overlap, image type. There's different IVO calibration levels from raw, which is a calibration level 1, processed single epoch observations, which are level 2, and co-added, which are level 3, calibration level 3. There's the band, and there's also time. Band, however, is used a little bit differently here, I think. I think it's in this case. Let's get to it. You can query by position. There's a whole lot, if you query for a given position, you may get a whole lot of data. So we generally don't recommend querying only by position. In this particular example, we'll limit the number of records returned to 3, a maximum number of records returned to as 3. You can define things within a circle, within a max-min RA-dec range, or a polygon. Here, let's look at we'll look at here at a circle of 0.05 degree radius. We define that using a tuple, a Python tuple, and then we query the SIA service, and then we will take a look at the results. And what we get are the object. In this case, a raw image, calibration level 1. Some of the things in the extended to Chandra Deep Field South are misnamed as SLU ICRS. They really are in the extended Chandra Deep Field South. So you may need to just ignore some of these at some times. And if you go further down, you get like the access. This is very important, the access URL where you can access those images. There's the format, they're in the format of a data link. And there's the filter name, filter wavelengths in meters, all the way, and it also gives like a polygon for the region that is being explored or has been where it lies. And so we grabbed we had 3 return, but okay, we'll keep this circle thing defined as before, but we'll delete the results for now. There's also examples for doing other bounds like min-max or polygons. We'll ignore that for now. Now let's look at the image type. Like you mentioned before, there's different calibration levels that are associated with the the IVO standard for SIA2. There's the calibration level 1 is a raw. Level 2 would be like a process image, like a single epoch image, like a visit image. And calibration product 3 would be a co-added image, like a deep co-add, a template co-add, or a difference image. Actually, that's not a well, that's actually it's not really a co-add, but it's a level beyond a single epoch image. Rubin only has visit images as their for catalog level 2, so you don't need to worry about that. You just ask for the catalog level, and you can get the results for that. And there's 1,656 in that particular point in the sky in that circle for a within 0.05 degrees of that particular RA and DEC in the ECDFS. All different filter types. You could actually give a subtype, but that's not very necessary for the visit images here. You can do something similar for deep co-add images. Those are catalog level 3. But here you do need to say the DP subtype because there's deep coads, there are there's template coads, and there are the difference images. So we can do that. I think it's like 12. Yeah, there's 12 of these. And we won't bother looking at the results. And you can also print the number of unique values of in each filter. So we'll see there's actually 2 coads in each filter, and that's it was actually because it was chosen so that it's like an area where there's there's overlapping patches between two coads. There's a little bit of each coad has a little bit of extra at the edges, buffer, sort of a buffer area around their perimeter. So then we can delete those results. You can do the same thing for template coed images and difference images, but we'll kind of skip that for now because we don't have a whole lot of time here. You may wish to query on band in the IVOA SIA2 service. Band is not really necessarily the letter name of a filter, but it's a wavelength range in meters. So we can define band edges for the LSTC filter curves based upon their filter transmission curves. And these are in meters. So it's 3 times 10 to the minus 7 meters, or 3,000 angstroms to 3932 angstroms for U band, and so on. And so we can define, so if we want to like grab, say, oops, let's run that cell. And let's say we'll do this so we can get R and I band. And then we can query the query for that circle that we had defined before, and a band for this caliber level 2. This is the visit images. And then print the number of R and I band images returned. So there's 321 I band images returned and 466 R band images returned. We delete the results. Oh, you can also just give a number. So like G band 5,000 angstroms is basically in the middle in the G band. You can just say you just give SIA2 service will return all images with a band pass that overlaps that wavelength. So you could just do that too. And there's 414 G band images in that circle. And we'll delete those results. Like we saw before for the Butler, you can define times in the TAI, International Atomic Time format standard. And you can query for visit images that are in that circle and in that range and in that time range. Yeah, this is for a 24-hour period starting on November 9th of last year. And there's 131 images in that time that were taken on that 24-hour during that 24-hour period. And then, okay, here's the meat of it. Okay, you got the information, you got the data, you grab you have the data access URL from those queries that you made. Now you can actually grab that data access query and then grab the actual image URL, and then you can read the entire image into what's called an exposure F object, which contains the image and the variance image and the mask plane and so on. This is exposure F format is designed to work well with seamlessly with the AFW.display function, and is recommended for all Rubin images. So you can read that URL into a visit image, and this takes a few seconds to run, and then you can display it in over here, and you'll see that it's popped up over here. Now here you'll actually notice that there's a lot of different colors here. This is from the different masks, and like a detected mask or or cosmic ray, various other masks. We can set the mask transparency to 100 so that you don't see the masks anymore. Oops, oh, and that is basically it. We don't, do you have any questions after this one? Any questions or comments or any difficulties? Like I said, once again, we're going pretty quickly, but hopefully people can follow along and use these notebooks later. All right, let's see. Okay, this one is sort of we're gonna skip over this one. It's 103.3. People are encouraged to look at it later. Oh, the cutout service. This is I'm gonna do this. Try to get through this one and the next one very quickly. So let's do I'll kind of speed through this. Basically, this notebook demonstrates how to use the image cutout service with DP1 images. The cutout service performs image cutouts remotely on the server using a protocol for remote data processing operations provided by the IVOA. I won't go into any detail. You read this on your own, just so we can speed through here, but just kind of to show you what you can do. Oops. Oh, let's see. So we'll import various import a lot of things, and we'll set the default backend as matplotlib. Well, in this case, we won't be using the Firefly URL output to the screen. We'll initiate the SIA service. We will find we'll use SIA. We'll use SIA to find the targets find the images that we want. We're looking again somewhere in the extended Chandra Deep Field South, and we're looking at, I guess, we're looking at R band of. So we're looking at a effective wavelength of about 622 well 6,221 angstroms, and we're looking at a particular short time frame on a given night to find this one I guess one image here. So we use the circle function, and this will return one object. And we can take a look at what that object is. It's okay. We won't delve into that because we want to kind of move quickly on. You can also query the images via tap, but we'll skip that for now. But it shows you how to do a tap query here. Now we'll generate image cutout. So we extract the data link using the access URL from that what was just returned from the SIA2 query, and then we'll provide authorization for the current RSP session because Rubin DP1 imaging is proprietary, and we'll do this using the get PyVio auth function. And then we'll create a data link results object to be able to access this URL, which will be stored as a data link result and available for approximately 15 minutes, a format that can then be used by IVOA tools. This data link is a VO table diagram stored as a DL result. So I'll grab this. Now we'll call the Rubin image cutout service. This is the IVO procedure cutout-sync that is called using this method here. It's done by feeding the data link created above to from resource. Let's see, since the Rubin DP1 imaging is proprietary, it is necessary again to provide the authorization using the get PyVio auth function. And so we use a SOTA query to do this. Now this variable holds the results of the SOTA query using the data link, which currently still points to the full LST visit image at its remote location in the database. And the cell below I'll demonstrate how to extract a cutout from this. So we'll define a sphere point to a radius of 0.01 degrees, circular sphere point. It will return, even though you're in a circle, it will return something with 4 sides. So we create a sphere point, and then we retrieve the cutout using this method. And it'll display it. And there it is. Nice, pretty galaxy there, galaxy group there. Now you can save it to disk if you wanted to. And before we used a circle, you also use a polygon. Yes, you also have to worry about correcting for cosine deck. But we won't go into that detail here at the moment because I do want to briefly go through the next tutorial. Any questions or comments for this tutorial? And I admit it went very quickly and we kind of skipped over a lot. But we think it's probably it should be pretty self-explanatory going through it again. But if you have any questions at this point. All right, let's go to the final notebook tutorial. I think we're probably not going to get to the portal tutorial, but let's go to the image display with Firefly. And once again, go to the tutorial tab, go to the DP1 menu, the 100 level sub-menu, the 103 level sub-menu, and go to 103 -5 or underscore 5 underscore image display with Firefly and click on that, and it will open up in your Jupyter environment. Okay, so here we're going to take a little more close look at what the tools over here. And once again, Firefly is just a little background. Firefly was developed at IPAC at Caltech, and it's a very nice tool. It has many aspects similar to SAO image. Let us just quickly dive in here since we only have about 5 minutes left. So we'll just import these packages and start up Firefly. Well, it's actually already started up. We've already moved, if you followed before, we've already kind of moved it over to the side. And we'll display an image. We'll query an image and we'll using the butler, and we will display it. And let's move this over here so we can see this better when it pops up. And you'll notice there's a whole bunch of stuff on top of it. There's a lot of this is a deep coad. So this has a lot of masks showing a variety of things, including the positions of the visit detector, the visit images that went into making this coad. And since Rubin is an alt-az telescope, the fields rotate. So all the images are going to be kind of rotated around and so on. And so you get a kind of a nice big lots of information there. As we saw before, you can set the transparency of the mask to 100% transparency, so you just see the image. You can change the scale. You can either through the notebook or over here. You can manipulate the mask and change the transparency to say 50%, so it's there, but okay, that's pretty, I don't know, it takes a few seconds. Maybe it'll, I don't know. It's a lot of masks there. You can get information on the individual masks. So these are bit masks like in SDSS images. You have like DAD pixels, clipped data, cosmic rays, crosstalk, detected negative, and you also have the colors and their values of their binary bit. So bad would be 2 to the 0th, clipped would be 2 to the 11th. Cosmic rays are 2 to the 3rd, and you can add them up; they don't overlap. There's saturation, sensor edge, so on and so forth. You can look at it here, but you can also come over here and you're this thing that looks like a bunch of sheets on top of each other, or like a book. This shows you the different levels. Oops. All right. Unfortunately, well, that's working. I'm having a little problem here. I had a little problem earlier today. This is not showing. Well, okay, here we could. There's different layers. There's the image, there's a sensor. You can turn these on or off, and you'll notice so say saturated. So you have saturated things like on the bright stars. A sensor edge, that's the edge of the detectors that went into from the visit images, and so on. Let's close that. You can turn off. You can once again set the mask transparency of everything to 100%, but then you can maybe readjust the detected image mask to 80%, and this will take a few seconds, but it'll pop up. It should pop up at some point. Sometimes it goes takes a little bit of time. All right. Well, maybe we won't wait. Sometimes it's also a little bit flaky. Oh, and then here's let's see. You can change the color of these masks. Sometimes it takes a few seconds, but we don't really have a few seconds left. You can also over here change the colors of your masks. Let's see other stuff. Oh, and then finally, you can also plot markers on the image. So why don't we find all the objects that are detected in this image using the Butler. And I won't go into detail, but we'll just grab from the Butler all the objects, and then we'll just display them on top of and so zoom in, you have all the detections marked. Oh yeah, here it mentions why are there nothing. Let's zoom out again, and you'll notice there's nothing at the edges because there are buffers between the patches, and I believe these were what were used to be called. We used to have a flag of is primary, or which has been now removed because we just only provide the is primary detections. But yeah, you can read a little more about that there. And I'm a little bit over time, and I went very quickly. But do people have any questions or comments? All right, I will note, and we don't have time to go over it now, but I think there's also a portal tutorial on using Firefly, in which you can like plot many objects together and so many fields together and look at stuff that way. But yeah, we unfortunately no time to do that, but it's a fairly straightforward tutorial to go through on one's own. All right. Well, maybe I should turn things back over to Melissa, as this was the final session of the school, and I'd also like to thank Melissa for all the organization that went into setting up the school. She did an amazing job, and I don't know how we would have done it without her guidance.
Yeah, thank you, Douglas. It was a team effort. I didn't make a single presentation. This whole Data Academy, it was all you guys. So yeah, thanks very much for doing all the presentations. We can take literally any question. So if it's not related to what Douglas was talking about, but anything else, you got a blocker, any general Rubin questions, we can also do those now.